This podcast is made possible by the Horner Prize for Blind Ambition, organized by the San Francisco Lighthouse for the Blind.
Professor Jonti Horner is an astrobiologist based at the University of Southern Queensland's Faculty of Astrophysics. He has had a keen interest in the stars since age 5. Professor Horner's area of expertise is small and transient objects in the solar system, from comets, asteroids and meteors, centaurs and Neptunian trojans. In more recent years, he has expanded his interest in astrobiology and the study of exoplanets.
Okay, good afternoon. Today we've arrived at the University of Southern Queensland to meet with Professor Jonti Horner. How are you doing, Jonti?
It's good to be here. It's good to welcome you to the campus.
Thank you very much. It's very hot today. It's summertime over here as compared to the Northern Hemisphere. Okay, so Jonti, how about you tell us a bit about how you started this journey?
Yeah, so I got very, very lucky when I was a kid. My parents had recorded a film for me, and this is back in the days of VHS tapes, back in the olden days. And at the end of the film, or at the start of the film, I can't remember which one, they just caught a bit of a TV show called The Sky at Night, which was a big astronomy programme in the UK that at the time was presented by this big old fat guy with a monocle called Sir Patrick Moore, who'd been presenting it since the late 1950s. And it was the longest running show anywhere on the planet with a single presenter, and he presented it all the way through till his death a few years ago. And he was this big ebullient enthusiast for science, and I guess to Brits he was the equivalent of the impact that someone like Carl Sagan had for Americans. And I just got hooked. I was 5 years old and I thought this was the most fascinating thing ever. Really got me obsessed with space, really fascinated. And my parents were brilliant. They were really supportive and took me everywhere I wanted to go and bought me books, and I got a telescope. And I joined my local astronomy society, the West Yorkshire Astronomical Society, at the age of 8. And that was really revelatory to me because it meant I got to share this wonderful hobby with lots of like-minded people. But I got to see every week people talking about it, giving talks, giving presentations. About once per month that'd be a talk from a professional astronomer like myself nowadays. The rest of the time it was just the members talking about what they were doing, what they were interested in. And that meant I got to learn a whole heap of things. It also meant that I got to cut my teeth fairly young in actually presenting and talking about my interests in my work. So I actually started giving outreach talks when I was about 10 years old, and that was really useful and had really stood me in good stead, much I didn't realise it at the time, because it meant I started doing these things before I got to the point of being a teenager, of being embarrassed. So I actually got to get used to doing this, really enjoy talking about what I do without ever having that embarrassment and that kind of cringiness that goes around it.
And so you were also making a lot of friends and, kind of creating a lot of fans before even the era of social media.
Oh, this is way back in the day. This is the late 80s and early 90s. I think I joined YAS shortly after Halley's Comet was visible in 1986. I was 8 years old then. Joined YAS and went from strength to strength there, and I even did things like I was on their quiz team. We used to have quizzes where we'd go to the other societies so they'd come to us and stuff like that. Really good fun, and I was probably the youngest person in the society by 20 or 30 years most of the time, because most young'uns would rather be doing other things than going out talking space. And the society had a really interesting membership demographic actually, because you get some younger people coming along joining up until the point they got to kind of 16, 17, 18 and discovered alcoholic drinks in the opposite sex, and then they'd vanish for a few years. Then they'd have kids and then discover that it's good to escape occasionally, and then they'd rejoin the society when they were a bit older, and you'd have this kind of gap when they went out and lived a different kind of life.
Whereas you just kept going.
Yeah, I just kept going, All the other stuff's fun, but it's been astronomy all the way.
Wow. So, yeah, Jonti, you actually have an impressive body of work, and I've seen that you had a lot of articles which talked about bodies in the solar system and which specifically have a relationship with Jupiter. One of those papers was actually categorizing different objects, going from centaurs. Could you explain what a centaur is?
The centaurs are a relatively new population of bodies in the outer solar system. They're not new in terms of the solar system, they're just new in terms of our understanding of the solar system, our observation of it. The first one is called Chiron, named after the mythical centaur, and was discovered in 1977, and they quickly found pre-discovery images dating back to the late 1800s, where it had appeared on photographic plates and never been identified. And what that let them do was work out very quickly what path the object was following around the sun, and they realised that it was really odd. It was clearly big, a couple of 100 kilometres across, and it was moving on a fairly circular but not totally circular orbit between the orbits of Uranus and Saturn, kind of crossing both, approaching both of those planets. And that is a kind of orbit that is just inherently unstable, doomed to death, doomed to ejection, doomed to chaos, which suggests that the object hasn't been there very long and won't be there very long. And it became the prototype of this class of object called the centaurs, which are many hundreds of objects. By the time we find them all, we're probably talking tens of thousands, that move around on these unstable, chaotic orbits in the outer solar system, with perihelia, their closest approaches to the Sun, somewhere between the orbits of Jupiter and Neptune, on orbits that approach or cross those of the giant planets. And they're really interesting because they are probably the parent objects of another group of objects called the short-period comets, things like Comet Encke, Comet Tuttle. Some of the comets that go around almost as regular as clockwork every few years. Those comets again are very short-lived. They crash into the sun, they fall into planets, they disintegrate, and they get ejected, all on very short timescales. So they have to be replenished from somewhere or there wouldn't be any left. And we think the centaurs are the population of objects that replenish the short-period comets over time. And in much the same way, we think the centaurs themselves are replenished by populations further from the sun, different, more stable objects that get scattered and introduced to become new centaurs, replacing the ones that go away.
So when you say centaurs are actually parents of smaller objects, so short-period comets, is it because they collide with another object somewhere and then they turn into different bodies? Because you were talking about the distance, the outer belt, and how their orbit goes between Jupiter and Neptune. Am I right in saying that? Or?
Yeah, so the centaurs themselves are between Jupiter and Neptune. The populations that feed into the centaur region include the Jupiter trojans, these objects trapped in Jupiter's orbit, but probably primarily the scattered disk, a group of objects out beyond the orbit of Neptune. And collisions in the scattered disk might play a little bit of a role in throwing new things into the centaur region, but mostly it's periodic, long-term nudges and pushes by the planets that change the orbits of these objects until eventually they scatter into that region. And it's the same thing for the centaurs becoming short-period comets. It isn't physical collisions, but you could almost think of them as gravitational collisions, coming close enough to one of the planets that the orbit of the small object gets flung onto a different path, changing its orbit. And the net result of that is that these centaurs, on timescales of millions of years, really bounce around the outer solar system like billiard balls bouncing around a pool table. They're deflected all over the place, with the end result that probably about a third of them will eventually at some point be thrown into the inner solar system to become short-period comets. Some for very short lengths of time, others for really protracted long-term captures. And the comet Encke that I mentioned earlier on is possibly one of the last surviving big fragments of a centaur that was more than 100 kilometres across, that was captured into the inner solar system tens of thousands of years ago, fell apart and fragmented, and the debris from that fragmentation gives us a torrid meteor stream, which gives us meteors hitting the Earth's atmosphere for a third of the year. In other words, the Earth spends a third of its orbit ploughing through the debris left behind from that fragmentation, and that's what happens when you get a really big centaur trapped in the inner solar system.
So that is a centaur. And so what would the difference be between a comet and an asteroid? Generally speaking, probably not in their composition, but their behavioral pattern across the sky? It's
a really good question, and if you go back to the origins of the two terms, asteroids are things that look like stars but move in the night sky and are smaller than planets, essentially. They look like star-like points, and that's because they are not surrounded by any gas and dust. They're just rocky or metallic objects floating through the solar system. Comets, on the other hand, the bright comets that we can see with the naked eye can be really spectacular, and they've been known since prehistory. They are the thing that we see is this huge diaphanous object of gas and dust with a head and tail, or tails, that point away from the sun. The head is a coma. Now, buried within that gaseous, diaphanous, beautiful shroud is a small object that, if it was a long, long way away from the sun, would essentially look like an asteroid. It would just be a point of light. But the point of differentiation between them is that that object, the nucleus of the comet, has a lot of what we call volatile material in it. That's icy material, ice, carbon dioxide ice, methane ice, things like this. When it gets close to the sun, the surface heats up, and that causes those ices, those volatiles, to sublime, which is a beautiful word. It means that those ices go from being solid to being gas without being liquid in the middle. And they go away from the surface of the comet, they escape, forming the coma, the cloud of gas around the comet, around the nucleus, and then being blown away from the sun to give a beautiful tail by the solar wind. And as they sublime from the surface, they carry with them dust, which gives you the dust tail of the comet. So that's the difference in terms of how they look. And if we were talking 20 or 30 years ago, in the main that difference would be really clear-cut. Things would either be a comet or an asteroid. But there are some objects, and Chiron was actually the very first of these, that get a dual classification, that have been considered both asteroidal and cometary. So Chiron, when it was discovered, was a point of light against the background stars. I mean, it was out in the outer solar system, so we could expect it would be a bit icy. But it wasn't showing any activity. There was no gas, there was no dust. So it was given an asteroidal number, a catalogue number, and we do that for asteroids when we've studied them long enough that we can be very confident we know how they're moving around the sun. That's kind of a mark of honour that shows we really know the object well. Then as Chiron swung in closer to the sun, got hotter, some of the volatile material on the surface started to sublime. It got a bit of a coma, would have had a tail, but the tail was pointing away from the sun, so therefore away from us. And so it then got a cometary classification as well, because it now looked like a comet. And so what you're actually seeing is that we think of asteroids and comets as two separate things, but they're kind of like opposite faces of the same coin. They're part of the same distribution, and the line is very blurred between them. The reason we really separate them into two camps now is just because it makes our study of the objects easier. They're all solar system small bodies, they're all small things floating around in the solar system, but calling them comets or asteroids is really just a shorthand for us to say if they're more icy or if they're more rocky these days.
Okay, and so somehow they can also, there's a property called albedo that can be used to distinguish them as well, or
to some degree.
To some degree.
So the albedo is a measure of how reflective a surface is. So if you imagine a whiteboard like we've got in the office here, like you've got in classrooms around the planet, that reflects a lot of the light that falls on it. So you could say that maybe reflects 70% of the light that falls on it and absorbs 30% of it, let's say.
Yeah.
If you absorb 30% and reflect 70%, we say you have an albedo of 0.7. An albedo of 1 would be where you reflect every single bit of light that falls on you. An albedo of 0 would mean you absorb every single bit of light that falls on you. And people bizarrely have actually invented a material that almost has an albedo of 0. It absorbs all of the light that falls on it, which has problems because that makes it heat up, and apparently tiles of it get super hot and would boil water. If I saw a thread the other day on Twitter where somebody was saying what would happen if you lined your swimming pool with tiles made of this incredibly light-absorbing substance, and essentially your swimming pool would flash boil. It would release a cloud of chlorine gas. You'd pretty much kill half of your city. So you don't really want to have something in your swimming pool with an albedo of 0 because it'd just heat up till everything boiled.
Yeah, it's funny because a lot of these eternity pools tend to want to take that property and put black tiles.
Yes. And black tiles is good so long as they're not too black. You want a bit of reflectivity. And you're familiar with this on a hot day. The dark tarmac of the road gets blisteringly hot, and I've seen, again, a lot of things being shared, that if you've got a dog and you take your dog for a walk, on a hot day before you take your dog on the tarmac, put the back of your hand against the tarmac, and if it's too hot for you to touch, that means your dog will get poorly paws, will get hurt, so don't do it. It's the same thing. The road is very absorbent. It reflects very little of the light, which means it gets very, very hot. What's interesting about all this, though, is that the albedo tells you how reflective something is, and the darker an object is, to look as bright in our night sky, it must be bigger the darker it is. Because what we see is just the total amount of light reaching us back from that object. If you had something that reflected all of the light, then it could be quite small and still look quite bright to us. But the more of the light that falls on it absorbs, the less that it'll reflect, so the fainter it would be at a given size. And so in order to be the same brightness, it has to be bigger, to have a bigger surface area to allow it to reflect enough light for us to see it. And that causes one of the real problems we have studying some of these small objects, because we don't really have a way easily to measure the albedo when we first discover an object. We just see a point of light in the night sky moving against the background stars, and we want to know how big it is, we want to figure out what it's like. But we don't know what its albedo is, so it could be something that's quite reflective and quite small, or something that's quite dark and quite big. And it's only when we can get other kinds of observations where we can take the temperature of the object that we can actually figure out its true size, because the temperature of the object will be driven by how much light it absorbs. So the light that's reflected is what we see in the optical with the naked eye with our telescopes. If you measure the temperature, you're essentially measuring what fraction of the light is absorbed, and when you put the two together, you get a feel for how big things are. And this can be a real problem. It takes us to the narrative of a planet that never was. We could talk about Pluto. When Pluto was first discovered in 1930, it was said to be a planet because, given how bright it was in the night sky, assuming it was as reflective as a typical asteroid, that would make it the size of the Earth. But then as time went on, we got more and more observations of it and started to realise that Pluto isn't the size of the Earth. Maybe it's bigger than the Moon. Well, no, actually, maybe it's a bit smaller than the Moon. And gradually, as we refine the observations more and more, we realise that Pluto is actually remarkably reflective. And the reason it's reflective, we've learned over the last 20 years, is that when it's close to the Sun, it almost behaves like a comet. It develops a coma, it gets an atmosphere, and then as it moves away from the Sun again, that atmosphere turns to ice, you get snowfall, and the surface of Pluto is a very reflective frost, snow. So it turns out that rather than being a dark planet the size of the Earth, it's a relatively much smaller object, a dwarf planet, a trans-Neptunian object, a Plutino, named after Pluto, that is significantly smaller than the Moon and much, much lighter than either the Earth or the Moon. It's tiny.
There's still quite a bit of debate, I guess. Well, there's some people who still want to keep Pluto in the system of planets, and obviously the observations are actually going the opposite direction. It also has some interesting properties because it almost orbits around its kind of sister body object, Charon.
Yeah, this is a really interesting facet of Pluto, which is that it has an incredibly large satellite, Charon. It's also got 4 smaller ones, Kerberos, Nix, Hydra, and Styx, I think, named after various things to do with the underworld. But Pluto and Charon are almost like a double dwarf planet, because Charon is 1/6 the size of Pluto. What that means is that the centre of mass between the two objects is outside of the body of Pluto. If you tried to balance them on a seesaw, Pluto would be far enough away from the pivot that the pivot would be outside the dwarf planet. Now, in the case of the Earth and the Moon, which is the closest equivalent we have among one of the real planets, the Moon is 1/81st of the mass of the Earth. What that means is that the centre of mass of the Earth-Moon system is within the Earth, albeit it's quite a long way from the core of the Earth. So as the Moon goes around the Earth, in our normal terminology, what's actually happening is that the Moon is doing a big circle around the centre of mass, while the Earth wobbles a little bit around the centre of mass, wobbles around itself. With Pluto and Charon, that centre of mass is outside Pluto, which means that Charon follows a bigger orbit, but Pluto follows a smaller orbit around that centre of mass, the Barry centre of the system. So in many ways, you could probably consider them to be a double dwarf planet with 4 additional companions floating around with them.
It seems like there's this enormous amount of interaction going on between small objects, asteroids, comets, larger comets, centaurs, moons, planets. They all actually follow a certain kind of predictable pattern using those 2 terms that you've mentioned before, which are perihelion and aphelion.
Yeah, so these terms come from how we describe the orbit of something, the path it follows through the solar system. And again, as was the case with the Moon and Earth or Pluto and Charon, things move around the centre of mass of the solar system's barycenter, but for simplicity we just talk about things orbiting the Sun. That just keeps it easier, and we set things up in that way. So every object in the solar system moves on a path that is an ellipse, an oval shape essentially. One extreme end solution of an ellipse is a perfect circle. At the other end you get something that's unbound called a hyperbola. These are all different parabolas essentially. That's just a technical terminology for it. What that means is that as something's going around the sun, at one point in that orbit, when that orbit is somewhat elliptical, somewhat elongated, you have the point at which the object is at its closest approach to the sun, the nearest that it ever gets, and that's what perihelion means. It's just closest to the sun. The other point is the point at which the object is farthest from the sun, and that's aphelion, and that's on the opposite side of the sun. So if you have an object at perihelion and you draw a line in it through the sun from that object in space and keep going in a straight line, the aphelion will lie on that line as well. And depending on how elongated the orbit is, the aphelion might be only a little bit more distant from the sun, in which case the orbit's nearly circular, or it might be a really, really long way away and then the orbit is very elliptical.
And at which point is that a high eccentricity?
Yes. So the eccentricity tells you the degree to which the orbit is circular or non-circular. It's the ellipticity of the orbit. An eccentricity of 0 means you've got a perfect circle. An eccentricity of 1 means you've hit the point where the object will never return, where the aphelion is infinitely far away. So between 0 and 1 you have all the range of possible bound orbits, orbits where the object will always return, always swing past the sun again. So an eccentricity of 0.999 is very eccentric, and an eccentricity of 0.1 is only slightly different to a circle.
So what are the average eccentricities or orbital eccentricities of, let's say, those comets, centaurs, or trans-Neptunian objects? Are they very highly eccentric, and do they follow a course which we can still predict enough? I guess Halley's Comet is one example. We can predict when it's going to come next, but how much disturbance is there in that elliptical pathway?
It all happens over time. This is what happens because all the objects are going around the sun following their own unique paths. And if you only had the sun and a planet and nothing else, it will continue following that orbit forevermore. Nothing would change up until the point where the sun itself came to the end of its life. But when you've got more than just two objects, all of the objects have gravitational pulls that interfere with one another, and that can cause the orbits to change. And it's that change in the orbits that makes them hard to predict. Now, the objects that we have studied the longest, we have the best handle on how they're moving, we have the most certainty in their orbits. When we discover a new asteroid or a new comet and we've only observed it for a day or two, we only have a very rough idea of how it's moving. We know where it is right now, but we don't know exactly what kind of orbit it's on. The planets themselves are on orbits that are typically fairly circular. Mercury of the 8 planets is the one with the highest orbital eccentricity. The others are very close to zero eccentricity, very close but not quite circular. For the trans-Neptunian objects and for the comets, it depends which population you're in, and every object has a unique orbit. So the things in what we call the Edgeworth-Kuiper belt, a disk of material beyond Neptune that's very similar to the asteroid belt between Jupiter and Mars, both the asteroid belt and the Edgeworth-Kuiper belt typically have objects on orbits with eccentricities that are not too high, so maybe up to or around 0.3, maybe a little higher but not much. For the comets, the eccentricities can go as high as 0.99999 or even become greater than 1. So if you have a comet coming in towards the sun that gets a kick, a slingshot from one of the planets, that can increase its speed to the degree that once it's swung around the sun, it will escape from the solar system forever. It becomes unbound and then moves on an orbit with an eccentricity greater than 1.
So it's almost as if they take some kind of boomerang-shaped path. They come in, sort of get attracted a bit by some of the larger objects, and then reflected back out into a completely different direction.
Essentially, if you come close enough to one of the massive objects like the planets, you can get a very hefty kick because a planet exerts a gravitational pull on you. It accelerates the object, causing its speed to change, but also the direction of its motion to change. That changes the orbit, so once it leaves the influence of the planet, it's moving on a different orbit to where it started. And that's actually the main way that things like the centaurs are transferred to become the short period comets. It's the main way that the short period comets are removed from the solar system. They're flung away to the icy depths, never to return again, as a result of encounters with the planets.
So this is kind of really interesting, because this pure interactivity between hundreds of thousands of objects. So, as far as I know, we have the planets and their moons, but we also have over 780,000 objects between the inner belt between Mars and Jupiter, as well as the Kuiper belt. All of those objects are actually currently monitored by different systems across the world, such as the NASA Horizon system at the Jet Propulsion Lab, as well as multinational collaborations to keep a look at all of these objects. And you're saying their eccentricity can go from very low and so very circular to eccentric. So there is a certain number of objects that we have been able to monitor, but that we will never see again.
Yeah, there are comets that came through in the past that are heading out to the depths of space that we'll only ever see again if we go out to space faster than they're travelling. We have even 2 interstellar visitors that have been detected in the last couple of years that formed in different planetary systems entirely, were flung out of those planetary systems and just happened to fly through our solar system at a time when we were looking. We've got an asteroidal object, which was the first interstellar object we saw, which was 1I Oumuamua, and I probably pronounced that wrong. It's named after a Hawaiian deity of travel, I believe. And we've got a cometary type object called Borisov, 2I/Borisov, which was detected by an astronomer in the north of Europe originally, and is tearing through the solar system literally as we record this interview, before heading out to the stars again. And they'll be heading towards the distant stars with a speed measured in tens of kilometers per second. We'll only ever see them again if we travel out there faster. And because the space is so incredibly vast, we'll actually only see them again if we choose to see them again and go travelling after them to look at them. Otherwise they'll be lost in space.
So is there also the opposite, where an object might have been taking a very highly eccentric path from a different area of space and then came across the solar system and sort of got captured by the bodies of our solar system over time? Do we know of any object like that? I think there are a couple of properties that could give us some more understanding. I think it's the hill distance, as well as the hill radius, and the Lagrange distance.
So the hill radius is essentially the gravitational reach of an object. So it's a way of telling how close an encounter is in the physical sense, in terms of how much of an impact it has. Jupiter is the most massive planet, so it has a big gravitational reach. Its hill radius is about a third of the size of the distance between the Earth and the Sun, I think. Neptune has an even bigger hill radius because it's further out, so it can control a larger area of space. In terms of vagabonds from other systems being captured to the solar system, it's possible. It has probably happened at some point in the history of the solar system, but it's challenging because these things are coming in very quickly and have to transfer a lot of energy through the encounter. So you need the right encounter at the right angle with the right depth to happen purely by chance. And for each of these objects coming in, you only get the one shot because they pass through the solar system never to return. The thing is, so we've got an incredibly deep abyss of time in the past running away from us. We've got 4,500 million years, and in this deep time, pretty much anything you can imagine may well have happened in the solar system because there's so much time and so many objects for it to happen. We've been observing with the ability to identify interstellar visitors probably only for a few years, actually, to be surveying the sky widely enough that unless they're glaringly obvious, we'll find them, and we're starting to discover them. With the next generation of observatory, with LSST, the Large Synoptic Survey Telescope, we'll probably start finding dozens of them. And they're coming through at this flickering little instant that we occupy at the minute. You know, the current 100-year period out of a history of 4,500 million years. So even the very unlikely things could have happened in the past.
That's you mentioned some of the new technologies, and I think we are sitting close to the site of one of those really interesting programs, which is the Minerva Australis. I think Minerva Australis is a system which is a secondary follow-up analytical and characterization kind of group of scientists who take the data that comes from the Kepler and TESS satellites. So a bit of background on the TESS satellite. It has been launched recently, I think in 2018, and it's going through its second year to capture millions of the brightest stars in the sky as a continuation of what the Kepler mission was, which itself only was able to capture a certain amount of the sky. So the TESS has 4 different cameras, wide cameras, and what the Minerva Australis does, I mean, maybe you can give us some more information about that.
Yeah, so TESS is a fabulous mission. It's surveying the entire night sky, as you say, looking for evidence of planets around other stars. But where TESS and also where Kepler, the predecessor, fall over is that they tell you that a star potentially has a planet. It's identified the possibility there's a planet there, but you need to follow that up with other instruments, with other facilities to confirm that what is suspected is actually really there. And when you're looking at hundreds of thousands of stars, you're finding potentially thousands of candidate planets. It's a real challenge to keep up with all those possible planets coming in and to queue them up in order to tick the box and say, yeah, that's definitely what it is. And it's with that in mind that we built this observation facility called Minerva Australis here in southeast Queensland, about 40 minutes drive from the campus we're sitting on at the minute, just up in the hills near Toowoomba. It's a collection of 5 telescopes whose largest mirrors are 70 centimetres across, so they're fairly chunky pieces of kit. And they're basically a glass fan. They're collecting light from the stars that TESS thinks may have planets, and we're using that light, passing it into a device called a spectrograph to look for the telltale wobble of those stars that indicates that what we think are planets are really definitely there, and also to allow us to learn more of them. And we are working in partnership with NASA. We're the only observatory in the southern hemisphere that is 100% solely dedicated to following up TESS observations. Pretty much all the other observatories that can do this have other demands on their time. They have to do observations for other astronomers who are not working on exoplanets, but we have our own facility that we can use as we see fit. So we get to do this all night, every night when it's clear, which is really cool for us, but it's also really important because the kind of observations we need to do are not just point and click and done. You need to monitor these stars over periods of days and weeks and even months, observing them repeatedly time and time again in order to build up all of that evidence that makes you confident that what you found really is a planet rather than something else.
So it's really fascinating to see how there's this chain of different technologies and in different physical locations, as well as teams collaborating from across the world to actually create this sort of secondary and tertiary filter to make sure to validate basically that an object out there that we're observing, that we consider or believe or think actually through careful analysis is an exoplanet, is actually one, and it's being confirmed. I think the first confirmed exoplanet was 51 Pegasus, and is that one actually used still as a reference, and is there still a lot of work going on that exoplanet to further, understand more properties, more details, maybe methods that could come out of the new technologies that have been coming out since, that exoplanet system was discovered?
Yeah, we do try to keep going back to the planets that we find and learn more about them. And 51 Pegasi b is a planet that stars 51 Pegasi, is a really interesting case in point. It's not the first planet we identified around another star, but it's the first planet that we were confident was really a planet and that was going around a star like the Sun. The history of planets around other stars goes back hundreds of years and is littered with failures and mistakes and planets that never were, and is it, itself really fascinating. You could have whole separate 2-hour discussion just about all the things we got wrong. We found the first things that we now recognise as probably being planets actually in the late 1980s, but when they were discovered, they're planets that are more massive than Jupiter, and the people who discovered them were naturally very cautious, as scientists often are, And it was seen as being more likely at the time that these were what we call brown dwarfs. They were failed stars. They were too massive to be planets but too small to be stars. And we knew a lot of brown dwarfs at the time, so these discoveries didn't really make as many waves as you'd think they would. But looking back at them now, having gathered more data, they probably are planets rather than brown dwarfs. Then in 1992, we discovered planets orbiting stellar corpses, planets orbiting a pulsar, which is all that remains from a star having gone supernova, an explosion that should destroy any planets that the star has. So they were kind of unexpected. But 51 Pegasi b was the first thing that was definitely small enough to be a planet, whilst also moving around a star that was like the Sun, rather than a dull ember left behind from a stellar explosion. And that really was the dawn of this modern era that we're going through, the exoplanet era. And we've got better and better at doing it since then. It's really telling about the way that we do research, that research is by its nature incredibly multinational. It's science without borders in a lot of ways. So the collaborations you have that are finding these planets are not just researchers from one town working with each other. Our partners in Minerva Australis hail from all over the US and from China. We work with people in South America, North America, Europe, Asia, all over the place, all to pull data together, everybody looking at different aspects, so that we can learn as much as we can about our targets. And the interesting thing is, you think, well, what if you find an object that isn't a planet, it looked like one and it isn't one, is that disappointing? Well, in a way it is. It's one that you've shown isn't a planet, but that itself is a window into something else that's interesting going on. What else could it be? What could be causing that signal? So the TESS mission and the Kepler mission, while their main focus is exoplanets, and that's where a lot of us work, they do a huge amount of other science as well, ancillary science that comes out of it, everything from studying the dawn of creation to studying small objects in our solar system and all the things in between, all come out as added value from these primarily exoplanetary science missions.
So one of the base techniques, I think you mentioned spectroscopy, is the Minerva Australis, which I think also has a kind of a counterpart in Arizona or Texas in the US, which is called Minerva.
Yes.
Minerva actually means Mini Exoplanet Radio Velocity Array. So those, when we speak about radio velocity, does that have something to do with the Doppler effect?
It does. So there are many ways you can look for planets around other stars, but one that's been very successful and gives us a lot of information is where you take the light from a star, break it up into its component colours, and you'll look for dark lines across that spectrum. So every individual element, every compound, will absorb light at a very specific set of frequencies, very specific colours. And this gives you the fingerprint of that element or compound, and every element and compound has a unique fingerprint, a unique set of colours at which it'll absorb, and a unique set of colours, the same colours that if you put it in a tube and you excite it, you pass electricity through it, say, that it will emit at. And that's how you get the neon signs that grace wonderful exciting cities like Las Vegas. You've got a tube of neon, you pass electricity through it, you excite it, and it glows at those very specific colours, giving you those unique lights that you see. So you have the light from a star that has imprinted upon it this spectrum, this series of dark lines that tell you the chemical composition of its outer atmosphere. And those lines occur at very specific, unique colours that we can measure in the lab. We know exactly where they should be. But you then get the motion component of the star. If the star's moving towards us, all of the light from that star will be very slightly blue shifted. It's the Doppler effect. So light that is slightly red will become slightly bluer. And what that means is that the location of every single line in that star spectrum will also be slightly blue shifted. So if you'd normally measure that light of a wavelength of exactly 500 nanometers would have one of these lines, and you blue shift it a bit because the star's coming towards us, you'd measure that line at maybe 498, 496. The faster the star's moving towards us, the bigger the shift, so the further from the expected location that line will be. Equally, if the star's moving away from us, the light will be a bit redshifted, so that imaginary 500 nanometer line might be seen at 502 or 505 or even 550 if the star's moving really quickly. So by measuring the locations of these lines, identifying them and comparing them to what we'd find in the lab, you can measure a star's speed. That's all well and good, but what if the star's got a planet? As we said earlier on, the planet doesn't actually go around the star. In actuality, the planet and the star both go around their common centre of gravity, which means that when a planet orbits the star also wobbles back and forwards as it moves around the centre of gravity, which means sometimes it'll be moving a little bit away from us, sometimes it'll be moving a little bit towards us, and it'll periodically move from moving away to towards us to away to towards us, doing one lap in the time it takes a planet to do one lap. So if we can measure the spectrum of the star, we can watch those lines move to the red, then to the blue, then to the red again, as the star goes around the centre of mass. The period it takes for that wobble is the period that it takes the planet and the star to go around their common centre of mass, so it's the orbital period of the planet as well. That tells us how far away the planet is from the star. The further the planet is away, the longer its orbit will take, the slower the wobble will be. The more massive the planet, the further from the centre of mass the star has to be to balance that imaginary seesaw. So if you've got a tiny planet, the centre of mass is really close to the middle of the star, the wobble will be very small. If you've got a really massive planet, the wobble will be really big. If you've, instead of a planet, got a massive star, the wobble will be enormous. So measuring how big that wobble is tells you about the mass of the planet. Measuring the time it takes to do one full wobble tells you about the orbit of the planet.
Exactly. And I think in the history of exoplanet discovery, we found out that basically planets are dominant across the board. So in our galaxy, really there are planets everywhere. And they're also particularly common around cool stars. So cool stars being a certain star age, or let's say spectral category.
Yes.
So our own sun has a spectral category of G. So we wouldn't consider that a cool star. A cool star would be more towards K or M.
The sun is really at the warm end of cool stars. It's probably, as a star, a bit more massive, a bit hotter than average, but not by much. It's fairly typical. And when we're talking cool stars, we talk about sun-like stars and cooler. Now, in the main, what that means is we're talking about stars like the sun and stars that are less massive than the sun.
Yeah.
With the exception that stars that are coming to the end of their lives swell up to become red giants and red supergiants, and they're technically cool stars, but they're not good places to look for planets. Now, we found lots of hot Jupiters and hot Neptunes, and we found lots of them around the cool stars, but that doesn't mean that they're the most common kind of planet. It just means that they're the easiest kind of planet to find. Because we have a number of biases that make it more likely that we'll find a hot Jupiter than we'll find a cold Earth. Firstly, planets the size of Jupiter are bigger and more massive than the Earth, and so that means they create a much bigger signal for us to spot. If you're using the transit method, where a planet's blocking out a bit of a star's light, the bigger the planet, the more light it will block, the easier that is to observe. If you're using the radial velocity method, a planet the mass of Jupiter has a much bigger gravitational pull, with the result that the balance point, the barycenter, will be further displaced from the middle of the star, meaning that the wobble is bigger than it would be for a planet the size of the Earth. So it's easier to find big planets than small planets. It's also easier to find planets that are close to their star than planets that are far away. With the transit method, you're more likely to transit the star and block out some of the light if you're close in, but also you will block the light out every time you go around the star, and it's much easier to identify a planet that transits a star every 3 days than one that transits its star only once every 3 years. So it's much easier to find the planets close in. Similarly with the radial velocity, with the wobble, the shorter the orbital period of the planet, the less time you have to observe before you've captured 1 or 2 full orbits, before you can be confident what's happening. So when you put all of this together, both of the most successful techniques we have for finding planets at the moment are heavily biased towards finding big planets and towards finding planets that are very close to the stars. And when you put those two things together, that means that they find most easily hot Jupiters and the slightly smaller hot Neptunes. In reality though, for all we're finding them around stars all over the place, only around 1% of the stars that we observe have hot Jupiters. The majority don't. So it's not that those planets are the most common type of planet, they really just are the easiest to find. And as time goes on, as we get more adept at finding these planets and finding the ones that are harder to spot, we'll actually find that the most common planets are planets that are more distant and probably smaller.
And recently, there's been a compact system of super Earths, which are clustered around one specific star, apparently, that we can see it through the naked eye. And there's a specific algorithm which has been used for it, which is the McLaughlin effect.
Right, yep. So the Rossiter-McLaughlin effect is a clever little thing you can do if you can observe both the transits of a planet and also measure the radial velocity thing.
And that's what Minerva Australis can do.
That's what we can do with Minerva Australis. And so if you imagine you've got a planet going around a star that transits that star, it will pass between us and the star, and during the course of that transit, it'll move from one side of the disk of the star to the other as it moves around in its orbit. It's just like if you see an eclipse of the sun, or if you see a transit of Venus like the one that happened in 2012. The transiting planet begins on one side of the disk, works its way across, then disappears. And whilst it's transiting, it blocks a bit of the star's light, and that's why we see the star dim very slightly and then brighten again when the planet's gone. But the star itself is rotating, it's spinning on its axis, typically with a speed measured in tens of kilometres per second. Now, if you imagine your planet is blocking at any given instant a little bit of the star's disk, it might be blocking the side of the star that's rotating towards you. And what that means if we measure the spectrum of the star is if we were looking at the star without the planet in front, the dark lines across the spectrum would be broadened by the rotation. Some of the stars coming towards you, so the light is shifted towards the blue, and the line smears in the blue direction. Some of the stars rotating away, so the line smears in the red direction as well, and you smear out the dark line. The faster the star spins, the wider the line, the slower it spins, the narrower the line will be. But now you put the planet in the way, and with the planet you block a bit of the light from the star that is blue shifted. What that means is that the light is still smeared all the way to the red because of the rotation of the star, but some of the blue light that would have been smeared out is blocked by the planet. So you see the shape of the line will change a little bit. It won't be as wide in the blue direction as it is in the red.
Yep.
And that gives you the impression that the middle of the line has moved by an amount that you can measure. You measure a change in velocity of the star that is actually measuring the rotation of the star.
Yep.
Now, as a planet moves across, it'll block different parts of the star that are rotating with different speeds, and you'll keep changing the shape of that line. It's a really subtle effect, but what it means is that you can work out the direction in which the planet is moving compared to the direction the star's spinning. You can, for example, see whether the star's going around in the same direction as the planet orbits or the other direction. You can see the tilt of the planet's orbit around the star. And this is incredibly innovative because it starts telling you information about whether the orbits of the planets around that star are aligned with the star's equator or whether they're tilted. In the solar system, the planets are relatively close to the plane of the sun's equator. They're not bang on, but they're relatively close. Yeah. But we found planets that are misaligned, that are tilted by 90 degrees or more even to the plane of their star's equator. And that's telling you something about the history of that planetary system. It might be telling you that the planets formed from material that had a different angular momentum vector, a different spin axis to the one that the star formed from, and that would be really interesting. Or it's telling you that the planets have stirred one another up and flung each other around over the history of the system, which has caused their orbits to become tilted, and that's really interesting as well. It's about the only way at the minute that we can readily get this information, and it requires that perfect confluence of events where you've got a planet that's transiting a star for which you can also make radial velocity observations.
So there's a really multi-dimensional approach by using these different sensors, and it's almost as if you have this one kind of blob of light that's kind of being very dynamic, almost like water, very fluid, but with some certain repetitions that you can observe, and as well as those, as you said, the spectrum colors that can take different broad lines. So you would kind of plot it, let's say, into a 2D or 3D graph, like a contour plot, something like that. But wouldn't you have certain difficulties for finding false positives? I mean, there could be, different effects, like, for instance, satellite engineering, the quaternions that come out of the satellite that needs to kind of change its orientation over time as it rotates around. I'm not sure what the exact orbital distance of some of the like TESS, for instance, is, but wouldn't it be kind of affected, for instance, by the mass of the Earth and how, there's some eclipsing going on, some of the lights might also, affect the actual light curve which is coming in. There's a cleaning process basically.
Yes.
With the light curves that come through.
And it's one of the great challenges for this, because there are a huge amount of different things that can give you signals that you would think of as being positive until you learn more about them. Now, the systematics of the spacecraft is one of those,
Yep.
and they put a lot of effort in making sure that they remove any of those systematics. But you've then got a huge amount of things to do with the star you're observing.
Yep.
For example, with the Transient method, one of the common sources of the false positives that have to be removed
Yep.
is to do with the fact that space is full of stars, and your line of sight to your target star may also include other stars in that small area of sky, because no pixel is infinitely small. So there is a chance, and the chance is lower the smaller your pixels are, but there is a chance that there could be an eclipsing binary star in the background or the foreground.
Yep.
And so that star, dimmer than your target star, has two components eclipsing each other that cause the light to vary and you think there's a planet. For the radial velocity technique, there are many other things that can give you periodic variations. Stars themselves oscillate like a struck bell, and there are all these different frequencies that give you signals. The rotation period of the star, spots that are on the star, and all of this is buried in that data. So what we're doing as astronomers is essentially trying to gather as much data as we can from as many different sources as we can to bring together the evidence that makes a discovery incontrovertible, to rule out all of the other things that could be causing a given signal, until all you've got left as an explanation is that there are planets there. And that's a real challenge. It's why it's taken us 400 years and more since telescopes were first used for astronomy before we're able to detect planets around other stars. Observations are some of the most challenging ever attempted, and at the same time we're having to develop new technologies to do them. So we had two things going hand in hand. Neither the radial velocity nor the transit observations are the kind of things you could do with the naked eye. Even looking through a telescope, the changes are too small. So we had to wait for technology to develop to such a level that our cameras, our detectors, are strong enough, are accurate enough, are precise enough to detect those incredibly small variations. At the same time, we had to get big enough telescopes, we had to get good enough mathematical techniques, we had to develop computers to do the processing of the data. And all of this comes together in a very, very thorny problem where we're at the pinnacle of hundreds of years worth of development that's led to this point, and yet we're still only taking our first footsteps into this whole new ocean of exploration. We're right at the start of the exoplanet era, and I'm sure if we talked again in a decade's time, the discoveries we make will have revolutionised our understanding of planets and our place in the cosmos.
I don't think the TESS satellite actually looks at O stars, which are hypergiants, because they're way too bright, and the impact of that brightness, there wouldn't be any planet big enough to even occlude or create any wobble on
To be detectable.
to be detected.
So the OBA stars, particularly the O stars and the B stars, are the most massive stars. They're very short-lived. They burn their fuel. They're like rock stars. They live fast and they die young. They tend to be very hot, very bright. They tend to be bigger. Because they're more massive, if we could do radial velocity observations of them, then you'd need a more massive planet to have a detectable signal anyway. But because they're so hot, there are very few spectral lines, so we can't do the radial velocity observations. For the transit method, well, these stars are the scarcest in the galaxy to start with, so there aren't many of them to look at anyway. But because they're a bit bigger, again, you need a bigger planet in order to detect it. There will be O and B stars that are in the right brightness range for TESS. They'll just be a very, very long way away, and that's another of the problems because they're so distant. They're hard to follow up. There's a lot of challenges here. But people have historically focused on the cool stars that are like the Sun or cooler, because they have lots of spectral lines, because they rotate more slowly, because they're smaller. And all of these things make it easier to detect a planet of a given size than for the brighter, more massive stars. But there is this open question of how does the occurrence of planets and what kind of planets you get vary with the type of star. And we've got to be aware of the fact that we're biasing our own knowledge by choosing the stars that are really easiest to study. And so for 2 decades, people have been looking at A stars, the intermediate stars that are more massive and hotter than the sun, but not as big and bright as the O and B stars yet, to try and find planets around them. Now they're just about within the remit of the transit surveys because they're not that much bigger than the sun. But we can't do radial velocity observations for them because there's just no spectral lines that we can hook onto, and those that are there are too wide because these stars spin more quickly. But what my colleagues at USQ here have done is to study retired A stars. So stars that in their youth, in the prime of their life, were A stars, but have now evolved off the main sequence. They're coming to the end of their lives, they've swelled up, they've cooled, and suddenly, because they've cooled, they've got all these spectral lines. So people have started to say, well, we can't really get a feel for the abundance of planets around A stars directly yet, although we're moving that way with TESS and with Kepler. But what we can do is study the stars that once were A stars in the past and see what the occurrence of planets is like around them. And we've had a couple of papers come out this year looking at that kind of analysis, trying to dig into it because we want to expand the boundaries of our knowledge and look at stars that have not been studied before, kinds of stars, because that's the only way that we'll get a full picture of what the planetary distribution is. It's a bit like, I guess, if you want to get a feel for how life is distributed on Earth, you wouldn't just look in your own backyard or in your own city, but you've got to look at all the different ecosystems, at all the different environments to get a true picture. And at the minute, we've been having a bit of a biased picture. I guess it would be the equivalent for me of coming from the UK, of having initially been looking just at life in the UK, and we're now starting to look at Europe and the US, and eventually we'll study the whole planet. As our techniques get better, they open more different avenues for exploration up for us, which means we can sample more widely the full distribution of stars and planets that are out there. Yes.
But in terms of the stars such as the OB, A, and A's, I mean, if there were any planets which could have some form of life on them, they would have, the Goldilocks radius would have to be extremely big to kind of be able to take the sheer radiation of that star. I think there's some hot Jupiters which are close to these stars, which aren't even they're not even formations of molecules anymore, but just masses of atoms because they're just completely broken down. But as they get broken down, and once the star starts to cool off, as you said, those things can kind of turn into different other molecular structures. So go from hot Jupiters to maybe some other forms of material, perhaps. Or
there's a whole heap to unpack there. So in terms of the lives of stars, the more massive the star, the shorter the life. And as a first approximation, you can get your head around it by the fact that the mass of a star and its brightness are related to one another. The more massive the star, the more luminous it is. But it isn't just you double the mass, you double the brightness. As a rough estimate, and this varies depending exactly how massive the star is, the luminosity of a star is proportional to the mass of the star to something like the power 4. Sometimes it's power 3, sometimes the power 4, but we'll stick with the power 4 for the simple explanation.
Yep.
What that means is if you increase the mass of a star by a factor of 10, you increase its brightness by a factor of 10,000. That's important because increasing brightness by a factor of 10,000 means the star's burning its fuel 10,000 times faster. But being 10 times more massive, it only has 10 times more fuel. So the lifetime of the star will be 10 times more fuel divided by 10,000 times faster burning is 1/1000th as long. So a star like the Sun, one solar mass, would have a lifetime of maybe 12,000 million years. We're using the very basic approximation, and of course reality is a bit more complex. A 10 solar mass star would be 10,000 times brighter and therefore would only live for 12 million years. Now, it's not quite as simple as that, but that gives you the idea that the more massive the star, the shorter its life, and therefore the less time there is for life to get started and established on a suitable planet, and that's problematic. The other thing is, as you said, that the more massive the star is, the brighter it is, the hotter it is. So the further from the star you'd have to be, if you were a planet that was a mirror of the Earth today, you'd have to be further away to be the right temperature. And you're right, we have found hot Jupiters whose cloud tops are probably measured in thousands of degrees, where all compounds are broken down to the component atoms. Their atoms are beginning to be ionized, and certainly they're as far from habitable as you could possibly imagine. Now, if that star lived and then died, it would probably engulf those planets. But if you were to cool those planets down, let's say you could miraculously move them to the freezer. As you cool them, the chemistry would change because you'd start to form those molecules again. How you'd move a hot Jupiter to more distant in the system, that would be challenging. But Jupiter-type planets aren't really where we'd be looking for life anyway, because when we're looking for life beyond the solar system, we're really going to be looking initially for life like us. It's something of a bias we've got, but it makes total sense that if you're looking for something and you're trying to make the first ever discovery, it's a lot easier to look for something you know and understand than for something you can't even imagine. So therefore, when we're looking for life beyond the solar system, we'll initially look for life that is like life on Earth, because that's the only example of life we've got. And in order to do that, we'll therefore look for a place that is as close to the Earth that we know and love as possible, because that's the one place we know you can have life. And what I need to stress with that is that we're not saying you couldn't get life in other places, and we're not saying that you couldn't get different forms of life. All we're saying is that initially you want to follow the targets that give you the best chance of success, and you have the best chance of success when you're looking for something that you already know can exist and that you know vaguely what to look for. So that will drive us towards Earth-like planets, probably around Sun-like stars, with environments and in planetary systems that are more similar to our own than dramatically different. And yes, that's bias, we're biasing our observations, but we're doing it to try and maximise the likelihood of a good outcome in the shortest time possible with the least wasted resources as possible.
Because there are approximately 200 million stars still to observe with the few missions so far, like the TESS. 200 million stars, that's a lot of stars to observe. And how many?
So we are really only scratching the surface here. The Gaia mission is an incredible mission. That's going to measure the distances to and motions through the galaxy of the 200 million stars you're talking about. That is only 0.5% of all the stars in the galaxy. We have probably 400,000 million stars in the galaxy. So even though Gaia is going to be surveying 200 million stars and has the potential to find planets around them, it's still a drop in the ocean, and that's just in our galaxy. So we really are very much at the dawn of this as a science. We've found currently just over 4,000 planets, but we know from those 4,000 planets, from the observations Kepler and TESS have made, that planets are ubiquitous, that planets are everywhere. So for the 400,000 million stars in our galaxy, they'll all have planets. There will be trillions of worlds in our galaxy alone, and there are more galaxies in the universe than there are grains of sand in our galaxy. And so what that means is that the 4,000 worlds we've found so far, it's like you're going around the Earth to interview every person, and you're still talking to the first one, and you've got 7 billion more to talk to. We're just at that dawn, that very start of the project. And that's immensely exciting, but it does show how much further we've got to go, and that's why, much as I would love to find evidence of life within the next decade, I won't be panicking and saying that we're alone if we haven't, because we'll still be just scratching the surface even then, and it's a search and a journey that's going to take us decades and hundreds of years. Maybe one day we'll actually be going out there amongst the stars and cataloguing them more close up, but initially we're doing it from this little moving platform of our planet, looking into the cosmos and kind of hoping we find that something's looking back.
And we shouldn't be discounting hot massive stars either, because maybe there's one of the properties which could be interesting is that the obliquity of the planets which are going around those massive stars to try to bring it back have kind of an architecture which is close to our solar system.
Possibly, we're still scratching the surface, so we still have a lot more to learn. Planets around hotter stars will not be the first place we'll look for life, because the lifetimes of those stars are shorter. And if you think about the Earth has probably been habitable, give or take, for more than 4 billion years, for more than 4,000 million years. But the earliest evidence of life we have on Earth that is widely accepted is in the Pilbara Craton in Western Australia, and it's these fossilised remains of life that is 3,500 million years old. which is incredible, but what that's telling you is that between the Earth becoming habitable and the evidence of the earliest life on Earth is a period of hundreds of millions of years. It's likely that there was life there at that time, but it didn't leave a record. What that means is even if you get life going immediately, it takes time to become well enough established for us to detect in the historical record. And it's likely also the case that on planets around other stars, life will take a long time to get sufficiently established for us to detect. So there's not really much point looking at a planet that is only 10 million years old. It may not even be habitable yet, but even if it is, has life had time enough to develop and thrive there for us to detect it? Probably not. They might be the kind of places where in the far distant future of our science fiction imaginings we could go and visit, because there would be benefits to building factories on a planet around an incredibly luminous star. I mean, the amount of solar power you'd be able to get would be great. Planets around very young stars would probably be incredibly rich in heavy metals and stuff like that, because the universe is continually being replenished in those materials with every generation of stars that lives and dies. But this is very much going forward to a future of us as an interstellar species, which is far beyond where we are at the minute. It's interesting to think about, but it's a long way from what we're doing in our day-to-day work. And when we find planets around other stars and try to search for life on them, we will have to pick the very best targets for that search. And to do that, we'll need to whittle down to the most promising ones, and I think the Earth informs that decision. We can look at the different factors that have made the Earth more or less suitable for the development of life, and then we can test them in our thought experiments, in our computer experiments, test them to destruction. And on Earth, there's a huge variety of factors that have made the Earth suitable for life and maintained that habitability. It's everything from where we formed in the galaxy to the neighbourhood of stars that we formed in, to the behaviour of the Sun, the other planets in the system, the small objects, and the Earth itself, and these all contribute. So on the one hand, you've got the Sun, it's a source of life on Earth, it's a source of the energy that we use, and without the Sun, the Earth would be frozen and sterile. But the Sun is gradually getting brighter over the last 4.5 billion years. It's probably increased in brightness by 30%. That means that when the Earth was young and life first emerged, the Sun gave us much less energy. And if the Earth was the way that the Earth is now, we would have been frozen solid. This was the cause of something called the faint early sun paradox. The idea that how was the Earth habitable when it should have been so cold as to be frozen? And of course the answer to that is that the atmosphere of the early Earth was dramatically different to that today. It was a thick, woolly winter dooner essentially with a very strong greenhouse effect. And over the 4.5 billion years since, as the Sun has grown more luminous, life has stripped the dooner away. It's pulled the greenhouse gases out of the atmosphere, which if the Sun had stayed at constant brightness would have caused the planet to cool and freeze. But because the Sun was getting more luminous, everything just happens to have balanced out and has kept us about in the sweet spot climatically, with a few cases where we've fallen off the rails and we've had snowball Earth episodes and stuff. Plate tectonics has played a role. Plate tectonics has maintained the Earth's atmosphere because life and weathering remove gases from the atmosphere, trap them in the surface of the Earth, and on timescales of millions of years that will gradually cause the Earth's atmosphere to precipitate out onto the surface. Plate tectonics recycles the surface and puts those gases back in the atmosphere, but it has also played a role in maintaining the magnetic field of the Earth, which has protected us from the atmosphere being stripped away by the Sun and the solar wind. So plate tectonics has been really important. We have the impacts, things being flung our way that have caused mass extinctions, but at the same time have opened the door for new life to evolve, and certainly we probably wouldn't be sat here having this discussion had the dinosaurs not been helped into an eternity of darkness by the impact of a comet 65 million years ago. Mass extinctions happen, they wipe out life, but they create new opportunities for life to expand and thrive. And even from the climate side of things, the other planets play a role in modulating the Earth's climate. Over the last 2 million years or so, we've had these periods of glaciation and interglacial periods, the ice ages. And those ice ages are driven by very subtle manipulations of the Earth's orbit and the Earth's rotation that are the result of the gravitational pull of the other planets, including Jupiter, particularly Jupiter and Venus. And these cause Earth's orbit to flex until it causes the Earth to precess as it spins, it causes its tilt to change. And all of these things put together.
3% of of change in a period of 41 years.
It's around 41,000 years. It's a relatively... That's okay. It's a relatively small variation, and there's a number of these. There are 5 or 6 different periodicities between about 20,000 and 100,000 years. They all stack up to vary the average amount of energy we get at the poles, which changes the temperature there, causing the ice to retreat or to expand, driving the ice ages. Now, what's interesting here, and this is work I've done working with colleagues of mine at the University of California, Riverside over the last few years, is to say that, well, the planets we find around other stars will have different architectures, the systems will be different, the planets will be bigger or smaller. So all of these forces will be different, which means in Milankovitch cycles, these periodic variations will be different. Can we use that to help find the best targets, the ones where the variations are not too big and not too small, not too fast and not too slow? And we're doing that initially by testing the solar system to destruction in our computer software. We move Jupiter around and see what happens. What if Jupiter were nearer to the Sun or further away? What if it were more massive or less massive? And we can track the effect that those changes would have on the periodic variations of Earth's orbit and therefore of its climate. We can track the impact it would have on collisions by asteroids and comets. And we do this for the solar system initially and find that the situation is more complex than we could have possibly imagined, that Jupiter's role is far more complicated and mysterious rather than being a simple friend or foe. But at the same time, it gives us a base that we can work from.
Okay, so Jonti, in the previous section, we were talking quite a lot about bodies, the solar system, and then we kind of went outwards into exoplanets, other systems, and we sort of made a round robin circle because we understood that somehow, well, it might be good to look into our own backyard. And, well, there was one of those mythical characters, which is the centaur. It seems there was quite a lot of work went through on that at the beginning of your career. So we have something for you, and this comes from Debbie or Lasayan.
Oh, fantastic!
So she 3D printed it.
That's wonderful.
And polished it and everything. Apparently, it looks like a shiny piece of metal, but it's not that heavy. It's not that valuable. So
that's surprisingly lightweight. Yeah, that's awesome.
Yeah, and it's a buff one apparently.
Yeah, so. It's a lot buffer than I am, for definite.
So here, I guess in this section, I would like us to, if possible, focus on the accessibility of all of this. Because, I guess one of my first questions would be, have you ever seen a blind person actually work on astrophysics?
It's interesting. Before I spoke to you, it's just not one of those things that occurs to me, because I'm aware that when you have the privilege of whatever the privilege is, I'm white, I'm male, I'm heterosexual, I tick a lot of the boxes for privilege, and that means that I'm very unaware of the difficulties people who don't tick those boxes face.
Yeah.
And I saw this a little bit because I'm from a working class background, so I saw the advantage that people can have from a better background. But when a problem doesn't directly affect you, you don't see it until you're made aware of it. And so it just never genuinely occurred to me, not from ignorance or deliberate kind of malice, just I'd never thought about what it would be like to not be sighted and to still do this stuff. But since we've had these discussions, I'm aware that there are a couple of people in the astronomy community who are not sighted and are doing really interesting work. And it is really interesting to me when I listen to how I communicate and listen to the metaphors I use. The fact that I'm sighted and the way I see the world is so kind of deeply ingrained in my communication and the way I think.
Yeah.
It's really interesting to try and visualize what it would be like to do the same kind of work without that. And I've got real respect for the astronomers who manage to do that in a world that is not geared around making it easy for them. Everything we do as scientists is geared around making it easy for us using our sight.
Yeah.
And we're aware of things like colour blindness. So there's a poster behind you on the wall in my office here where I've got some figures that I made for a talk. And someone mentioned to me years ago, you're aware that if you use certain colours, are bad for people who are colourblind, they can't see the things, so you should use this particular map in a graphical package that uses a colour map that is suitable for colourblind people. Yeah. And so we do that. But it's still people who are sighted, they can still see. And you still make the graphs and you assume that everybody can see them. And you write a figure caption that allows someone to understand the figure, but the figure caption doesn't describe the figure in a way so that you can see it if you can't see it, kind of thing. And so it must be really challenging for those astronomers to build tools and to work around these things that everybody takes for granted. And like I say, it's not a deliberate thing. It's just until you're aware of the problem, you never think about how you solve it.
So one of the big imagery concepts I try to express as a blind person to sighted people is that imagine you've got a nomad in the desert. Basically, that nomad sees nothing but sand dunes everywhere. So in terms of imagery, it's a desert. It's literally a desert. And the nomad usually tends to really kind of navigate around the world using the stars, especially at night. So although perhaps that nomad might not have, the perfect mathematical toolbox in order to conceptualize maybe an idea, he has sort of this natural inclination to really use his intuition between what is around him and the small details that he can still perceive, even though he's in a place such as a desert, which probably is very hard to navigate through. So this is kind of how maybe we can transpose things which are normally visually oriented into something more sonically oriented. You can see the breadth and the how sound can also orient you in different ways. So if you listen, towards your left, then that stereo span can be somehow used as well to put, let's say, on the left-hand side, you'd be putting, the spectral lines in different bands, let's say, and on the right-hand side, you would kind of look at more, like in terms of time-based stuff, like the wobbles and the radial, velocities and the Doppler and things. So, what kind of challenge currently? What is the most challenging thing that you're going through currently with your work?
Well, it's mainly actually finding the time to do the work. There's so much to do and so little time. And that's just, I think, a perennial problem. And with most fields, you have to work harder and harder and you spend more and more time doing it. I think in terms of data visualization, partially because we're so mired in the visual on a two-dimensional piece of paper, we tend to think in terms of at most plotting a three-dimensional space. So again, with the kind of figures that are on the wall in the background to you, I've got a two-dimensional grid and then a third dimension in the form of colour. And that's about as far as I've been able to go with it. And we have made a few animated figures where we make it a three-dimensional grid with colour, so you can get to 4 dimensions. But as someone who is interested in music, and I get singing lessons, I've got a very good friend who's an opera singer, I'm aware of how much information you can cram into a soundscape that you could use either to complement or potentially even with training, and it would take a bit of getting used to supplement or replace those kind of figures. And it would be wonderful if there was some way to deliver the kind of content and the kind of information that we put in our plots without thinking about it in an alternate form where you could get exactly the same amount of information without having sight. I could see that being an incredibly valuable tool both for outreach and communication, because not every student in a school is going to be sighted, not every person in an audience is going to be sighted, but also to the scientific community. And you could take it further in the way we recognise patterns in music is what drives tonal and dissonant sounds and things like that. We're very good at picking up very subtle shifts, which are probably, I guess, so subtle that if we put them into a visual form, we wouldn't see them. I almost get the feeling that we've got more dynamic range, more sensitivity in our hearing than we do in our sight. Probably, I might be wrong, but that's the kind of feeling I get when when a guitar's very slightly out of tune.
Yes.
But if those two notes were colours on a plot, you wouldn't be able to tell that the frequencies were slightly off. I guess that's what I'm thinking of.
Yeah. And this is the message I'm trying to drive through with the Holman Prize, is to kind of say, well, it's not just, empowering people with disabilities, or, I wouldn't even call it a disability, I would just call it a quirk. And, that quirk makes us focus on a different side or a different perspective, whether it's going to be, just mobility, education, work, or just social. And we have difficulties in each of them, but one which could be interesting and where we can really kind of become valuable is to be able to transpose everything which is normally visual into a whole kind of spectrum of tools which are audio signals. But the sound design would be important because you don't want it to be over invasive and just kind of really hurt your ears and things. So maybe if we could try to see here in, for instance, the categorization of transiting objects, whether it's going to be, short period, long period, the Trojans or, the centaurs, what kind of sets of information could I potentially use to say, well, this one is actually a short, this one's categorized as long or short, or, would it just be different tones to say, well, this is literally, a centaur. So if we scan into the sky and, kind of looking for objects, so imagine just completely take all visual assumptions away. I guess that's what Einstein did, right? So when he was asking his questions, he was taking all assumptions off. And, all right, what would be the best way to interpret the categorization of small objects?
I guess it's again thinking about how many variables you want to give for a certain thing, and then how best to display them. So, for example, if you're just scanning across the night sky, you have different objects, and you could break them down many different ways. But I mean, a simple way for a first separation could be self-luminous versus reflected light. As a really basic thing, because that gives you stars, nebulae, things like that, versus planets, rocks, things like that. Now, not necessarily saying you'd have a different note for the two of those, but a different quality of sound, whether it's a rough sound versus a smooth sound, a twinkly sound versus a guitar sound, whatever. Because you can then, for each of them, layer in the other things then to be the important elements of them. So for a solar system object, we characterize the orbit of an object by 6 numbers plus a time at which it's somewhere. And that says exactly where it is on its orbit or exactly where it is in space. That can be 3 dimensions of x, y, z for position and 3 dimensions of velocity in each of those. Or it could be the Keplerian orbital elements. We talked briefly about eccentricity earlier on, and there are 5 others that you'd use there. But in reality, to talk about what kind of object it is in the solar system, to first order, only 2 of those are relevant. You've got the semi-major axis, which is the distance from the star, essentially, which gives you the orbital period. So semi-major axis or orbital period. Then you've got the eccentricity, which is how circular or elongated the orbit is. They tell you the orbit. You've then got physical parameters. You've got the mass or the diameter of the object. You might have its albedo as well. But it strikes me that you've got enough variety in the sounds that you can make that if you have a type of sound that is clearly a non-luminous object, so a reflecting object, you could then have a volume for the diameter. You could have a pitch for the orbital period. You could beat for the eccentricity or something to give the impression of getting closer to the star. You beat faster, then you beat slower. There are all sorts of things like that I could envisage. And that's from my point of view as someone who is sighted, and so therefore I don't have the training to perceive the subtle changes as much as I guess you train yourself when it's more important. When it's such a big part of it. Because, I mean, I've noticed with the equipment you use, the speed of the speech, I can't discern what's going on because I've never trained myself to do that.
That's pure training. That's right.
And I think the more you develop down this, the more subtlety you can get, the more nuance, and the more you can get out of it. The other thing that occurs to me, especially with how technology is improving, is the degree to which tactility is important.
It is.
And you could combine the two. So, I mean, if that gives you an extra 2 dimensions of phase space, you can imagine having a device in front of you with something that responds to you so you can feel the tactility of where you are. And as you trace around on that, the location is the location you're looking at, and then the audio things are what's there, if that makes sense.
What I was starting to think about is that a graph is literally, the x-axis is usually the timeline, unless, you change the frequency dimension, and so it then becomes sort of a histogram kind of thing. So that the tactile aspect would be more important. But if you kept it on a time-based system, even in an accelerated form, you can actually pick up subtleties.
Yes.
A lot of people actually double or quadruple the speed of their audiobooks so that they could just keep listening to it very, very quickly. So maybe that kind of scrubbing along a certain timeline would be an interesting thing to do. But one of the problems that I've actually butted against is that when you take, let's say you take a light flux, you take a light curve, most of the times, even if you normalize it, that light curve is so dirty that when you try to push it out, as a sound, it's disgusting.
Yeah.
What kind of transformation would you see that would allow one to actually listen kind of on a more, less invasive way, kind of cleaner way, but still being able to pick up those small nuances over time by being able to scrub, let's say with a hand, or maybe you got like a circle or disc that you move left or right, just like a DJ turntable. But you can scrub through it, and you could stop at some point, scrub back, but very slowly to go, well, that seems to be an interesting position, and you tap a button, and you've got a marker.
That could be good for identification of things like transits is the immediately obvious one, where you've got a flux from the star that is a little bit noisy, it bounces up and down, but then when there's a transit, the flux drops.
Yep.
And you could do that in pitch or volume or both, and have that represented that way. You've also got, if you're looking at the orbits of planets, I'm thinking about the dynamics of a system.
Yeah.
Depending on the circularity or ellipticity of the orbit, the position over time or the radial velocity over time, if that's what we're measuring, can be more or less sinusoidal.
Yeah.
Can be more sawtoothed.
Yeah.
And when you've got multiple planets, you'd have multiple nodes.
Yes.
Now, one thing I think would be potentially quite beautiful is for those systems where you have tightly packed systems, they're usually resonant.
Mm-hmm.
And when they're resonant, the periods are all integer multiples related to one another. And that is very much what we have with music with chords.
It's harmonics.
It's harmonics.
Yeah.
So it strikes me that scrubbing through the catalogue of known multiple planet exoplanet systems, one of the things we're often doing as astronomers is trying to figure out if a planetary system is resonant, and we run simulations for that. But as a first look thing, if you get the 2 notes, or the 3 notes, or the 5 notes of the planets in there, the purity of the chord or the nastiness will give you a hint as to whether any of those planets in there are resonant. And I know there are people out there playing with this as a visualization tool. I don't think from the point of view of a learning experience, but rather as a thing of beauty. It's at the interface of art and science.
Yeah.
Earlier this year, in July 2019, we had the 4,000th confirmed discovery of an exoplanet.
Yeah.
And to commemorate that, a company called System Sounds, who I think are in the US, released a beautiful little video cataloguing the history of the exoplanet era in partnership with the National Exoplanet Archive, I think, where they have a visual which is a projection of the sky, which I guess could be your tactile thing under your hand if it's been 2 dimensions, X and Y, longitude and latitude essentially.
Yeah.
But then overlaid on that, whenever a planet was discovered, it ran through in time, a note sounded.
Yep. When it runs through the entire orbit.
Yeah, and the note tells you the period of the orbit, the size of the blob told you how massive the planet was, things like this, but you could easily do the volume of the note tells you the mass of the planet.
Yeah. Well, shout out to System Sounds.
That was wonderful, and I mean, it's worth people going and looking for it. It's freely available on YouTube and Epic. I don't know if you've had a chance to talk to them. But
actually, we're going to actually meet up in Canada during the US part of the investigation, so that we can actually try to combine art, creation, and science.
That sounds wonderful. I mean, I don't know what their motivating ethos is, whether it is purely from the artistic or whether they're driving in the same direction you are. But it struck me as a natural synergy. Their visualizations are beautiful, and you can give them the advice so that they can make it more accurate and useful rather than just pretty.
Yeah, we've discussed a lot about how to actually use sounds with tactile feedback by using infrared cameras and things, but that's going to come up a bit later this next year actually, because we're still in 2019.
Well, I can see with the development of VR actually, feedback from body position, if you've got sensors on wrists and neck and things like this, you get the whole 3D positional thing. So you can almost imagine somebody stood in a darkened or illuminated room with sensors, and as they move around, they're moving through the town soundscape. They can control with gestures that can be recognised in much the same way that people now control their phone with smart gestures.
Smart gestures, yeah.
And that way, you could it's almost like something out of a sci-fi movie from Star Trek or something. You have persons stood in the lab just swiping left and right and making things bigger, and the sound responding to that.
Absolutely. So that's one of the things. Do you think it would be now at this point, when we zoom in onto, I mean, with the current state of technology, when we look at a certain star, there's no way photometrically that we can actually figure out whether there's a trans. Because I was thinking of an idea to actually put sine waves associated to haptic feedback to take the astroseismology of a certain star, and as you keep your finger on there, with the type of resolution and graininess you can get, you sort of get a rhythm under your hand, under your finger. Yeah.
That would be wonderful. I was thinking, just so you're saying, that astroseismology would be a beautiful tool for this, because it's an incredible complexity in there that people typically try and approach in mathematical sense. It's this whole point that stars ring like a struck bell.
Yeah.
People often describe it as the music of the stars.
Yeah.
And I think a lot of it is identifying multiple frequencies at different levels with different noisiness, which we do naturally, orally. We just do that when we're out and about all the time without realising it. So it strikes me that probably the first, most natural, most obvious home for this could actually be the astroseismology stuff of the work that we know. And of course at USQ we will be moving into that area. We're putting new telescopes up at Mount Kent over the next year for a project called SONG, which is a Stellar Oscillations Network group. They are based primarily out of Aarhus University in Denmark, and they're kind of the world leaders in this. But one of my colleagues, Duncan Wright, who I think I've introduced you to, actually earlier on in his career was doing astroseismology work. So we've got connections there.
It would be great. I mean, if you could put us in touch, with someone when we go to Europe, so maybe we can sort of exchange information to see how that can actually move forward for people who are visually impaired, because I do really think, as I say, there's a conjunction between art, creation, the sciences, and again, different ways to perceive those phenomenon in the sky, and that might actually give really kind of, 280, 290 extra million people the capacity to explore the sky. So thank you, Jonti, for this interview. I'm really, really inspired by all the work, and I hope to be able to come another time so we can talk about a few of the other, papers and work that you're actually on, and see if you have some updates.
Definitely. No, I really appreciate it. It's been a pleasure talking to you, and we've got so much more to talk about. It would be fabulous if you could get back at some point on the Grand Tour and fill me in on how things are going, if nothing else. I'm looking forward to seeing what you learn.
Yeah, definitely. I have a lot to learn. I have a lot of weight to lose as well.
I'm exactly the same.
Well, thank you very much. And here is, what's her name already? Cosmo Bali, who's going to be visiting the different places with us. And, Jonti, hope to speak to you another time.
I'll talk to you again soon. Thank you for having me.
This podcast is made possible by the Horner Prize for Blind and Vision, organized by the San Francisco Lighthouse for the Blind.